Hello and welcome to the lectures on state space approach to control system analysis and design. The topic of this week is control design via desired closed loop response, and in that we are specifically learning the pole placement methods. The methods working on minimization of a quadratic performance index we will learn subsequently. Now in the last two lectures we have learnt what is the concept of feedback, state feedback and output feedback. We saw that state feedback results into a configuration in terms of classical control theory as a feedback path compensator, feedback compensator. We also saw that state feedback is capable of achieving any desired closed loop locations in the left half S-plane with the natural restriction of complex conjugate poles. We did pole placement using the companion form system matrices, and we found that it is very easy using the companion form system matrix. When the system is not in companion form, then it has to be first converted, transformed into the companion form, and thereafter the pole placement could be done. Now in this lecture we learn the following things. There are some pole placement formulae for single input systems. We will learn those two formulae. We will also briefly look at the pole placement for multiple input systems, and finally towards the end of the chapter we will try to address a question which is postponed from the beginning, that where to choose the closed loop system poles. So the considerations involved and some guidelines for choosing the closed loop system poles. Well, so we come to the pole placement formula for the linear time invariant systems with single inputs. Of course, we required transformation to companion form, and that transformation involves a little few steps, mathematical manipulations, which may sometimes look cumbersome, but that is necessary if we have to do pole placement using the companion form matrices. Now these formulae devised one by Ackermann and other Bass and Gura formula, these two formulae, they take care of that transformation implicitly, and that is why they are very useful in pole placement for single input systems, those systems which system matrices are not in companion form. So we first come to the Ackermann's formula, and according to this formula the gain k is given by the row vector, all elements are 0 up to n minus 1, and the last one, the nth element, is 1. And essentially it selects the last row of the matrix Q inverse. When this vector is multiplied by Q inverse, it will select the last row of Q inverse, and that multiplied by a polynomial in A. So the feedback gain matrix is given by the product of this row vector into the inverse of the Q matrix, and that multiplied by the polynomial in A. So Q is the controllability matrix, as we already know, and this dA is a polynomial in A, in which, of course, nth degree polynomial in A, in which the coefficients are d1, d2, etc., which are the same coefficients as the coefficients of the desired characteristic polynomial. So if the desired characteristic polynomial is ds equal to s power n plus d1 s to the power n minus 1 plus d2 s power n minus 2, etc. So we see that dA is the same thing. In place of s we have a, so it becomes a power n minus 1 here, a power n minus 2 here, and so on. So this dA is a polynomial in A, and the coefficients are the same as the coefficients in the desired characteristic polynomial for obtaining the state feedback gains. So we consider an example to where we will apply the Ackermann's formula. This is the same example which we have been taking throughout from the beginning of this topic. So this A is a 3 by 3 matrix and B is the one column corresponding to, of course, single input. And for this system, we want to obtain a state feedback gain K. Desired characteristic polynomial is same as the one which we have been taking, s cube plus 6s square plus 11s plus 6. We have been taking this. Probably it will be there in the next slide. So we want to design a state feedback gain K so that for this input matrix and this input matrix and this system matrix, for the system, the closed loop poles will be at minus 1, minus 2 and minus 3, and the corresponding polynomial closed loop system characteristic polynomial will be this. So as required in the Ackermann's formula, we have to evaluate the Q inverse, and before that we evaluate the Q, which is like this. This B comes here, this will be AB, and this is A square B. We have to evaluate. Then we obtain its inverse, which comes like this. This is the Q inverse. Now this is, I was telling, this is the desired characteristic polynomial, and so the dA will be, in place of s cube we have a cube, in place of s square we have a square, so 6a square. Here a in place of s, so we have 11a plus 6. This should be identity, 6i. So dA equal to a cube plus 6a square plus 11a plus 6 times identity matrix. So when we evaluate this for the given value of A, which was there in the previous slide, this is the A matrix. For this, if we evaluate this, we will get this. We obtained dA, we have Q inverse, so we will have K equal to that n by 1 row vector, 1 by n row vector, which is this. Only the last element will be 1, remaining all will be zeros. So that into this is Q inverse, and this is that dA. This is Q inverse, this is D of A, and this is the row vector that selects the last column of Q inverse. So when we evaluate this product, we will get this, which is the control gain required for this system to get the closed loop characteristic equation as this. So without any transformation to companion form, the pole placement, required pole placement is done. The design of K is obtained. So Ackermann's formula does that. Now everything is fine. Only one remark I want to make here. When we make use of the Ackermann's formula, this what we see is that we have to obtain this polynomial. We have to evaluate this dA, and dA starts with identity, then A square, A cube, etc. Now if the A matrix is not properly conditioned, if some elements are small, some elements are large, then what will happen is that the various a square, etc., we will get bigger and bigger numbers. Like we see here that a was, the largest element in a was 6, whereas when we evaluate this, the largest element is minus 120. Now you can imagine that if we have to apply this formula for some system of high order, 10, 15, etc., in practical systems we encounter very high order systems, and if we evaluate this, we are likely to face numerical errors. So Ackermann's formula, it may give not so good results, or it may fail to give results for large order systems. For small order systems, it is fine. Now we come to the other formula for single input systems. This is called as the Bass and Gura formula. And by this formula, the state feedback gain K is given as transpose of QW transpose inverse multiplied by D minus A. And in this various terms are, Q is, as already known, it is the controllability matrix. W is an upper triangular matrix like this. The elements are in the first row A1, A2, etc. up to AN minus 1, and A are the coefficients in characteristic equation, characteristic polynomial. So like we have ASN A1 s power n minus 1 plus A2 s power n minus 2 and so on. So these coefficients, they are put here to make the first row. Second row is this row pushed by one element. So this one comes here, A1 goes here, A2 will go here and so on, and it ends with n minus 2. Likewise the third row, etc., and the last row will only contain a 1. So it is an upper triangular matrix formed by using the coefficients of the characteristic polynomial, and Q is the controllability matrix, I told that. So we have to get the product of Q and W, we have to take its transpose and further the inverse of that transpose of the product. D is a column containing the coefficients of the desired characteristic equation. So D will be these coefficients D1, D2, etc. up to Dn. And A is coefficients of the characteristic equation of the system matrix A. So A is A1, A2, etc. up to An. So that D minus A is the D as I wrote this one, and A is this one. So D minus A is essentially the difference of the coefficients of characteristic polynomial of the terms n minus 1, n minus 2, etc. between the desired characteristic polynomial and the actual characteristic polynomial of the open loop system matrix. And so we have to evaluate and we get the control gain K for the system. We again take the same example, same A matrix and same B matrix. Q is this. This is the characteristic polynomial of this A matrix. And that means we have A1 equal to 9, A2 equal to 12, and A3 is 0. So we have this as this 9, 12, 0. D is the one which we are using all throughout. So if we put the coefficients D1, D2, D3, etc., we get 6, 11, and 6. So we got A from this, we got D from this. Now D minus A will be this. This is D, this is A. So D minus A is this. And so W we are assembling next. So W is 1, then this A1 9, and this A2 12. A3 is not used. Then we push it by 1, so this 1 comes here, 9 comes here, and we again push it by 1, so 1 comes here. So we get the W. Now the next thing is to get the QW transpose. So if we multiply and take the transpose, we get this matrix for QW transpose, this 3 by 3 matrix. So we take its inverse, and this is the inverse of QW transpose. Now this has to be multiplied by D minus A. So this is D minus A we had obtained earlier. This is QW transpose inverse. So product and then transpose of that. So we get the gain matrix this. So again, this Bass and Gura formula takes care of that transformation implicitly, transformation to companion form implicitly, and it works quite efficiently even for higher order systems. My personal experience, I have seen that. So now we come to the second subtopic of this topic, the pole placement for multi-input system, multiple input systems, meaning that number of inputs is more than one. I must tell that this topic is well researched and a very vast topic, and what I am going to tell is only just a sensitization to this topic, which will only bring a very small aspect of the whole topic. So we are given with a multiple input system, x dot equal to x plus bu, number of inputs is m greater than 1, and so B is n by m matrix. For this system, we have to design the gain matrix, and this is the problem statement. We have to find a k in u equal to minus kx plus r such that the closed loop system matrix has poles as the desired locations, or the characteristic polynomial of the closed loop system matrix AC will have the coefficients as desired. This is the problem statement. We have to find a k. Now what we have to do is we have to select an AC which will have the desired characteristic polynomial. So first of all, we have to select an AC. Once AC is selected, then we see that by changing the sides, BK taken this side, AC taken this side, BK will be A minus AC. A is known, AC is selected. So BK will be one n by n matrix. This BK will also be n by n matrix, but in that mn unknowns are there. K is m by n matrix, so mn unknowns are there, and we have total n square equations in this set. So what we have to do is, out of those n square equations, we have to take a consistent set of mn equations, and we have to solve them to obtain the k. And we see that because we have n square equations and we are only using from that the mn equations, so we have a non-unique solution. Several solutions will be possible depending upon how we pick up the equations and how we solve. That is one. Second thing is that several ACs, one can find different ACs which will all have the same characteristic polynomial. So there is no unique choice for AC. Multiple ACs will have the same characteristic polynomial, and so in case of a multiple input systems design of state feedback gain, we have all the possibility of non-unique solution. We see example. So we have this A matrix and we have this B, the input matrix. There are two inputs and we want to obtain the state feedback gain for this system so as to place the poles. Again, the same characteristic equation which we have been using. S cube plus 6s square plus 11s plus 6. Now we have to first find one AC which will have this characteristic equation. And for that we select this K has to be determined and we select this AC. This AC, you can see this is in companion form. So its characteristic polynomial will be the one which was shown a little while back. And this K, this 2 by 3 matrix containing 6 elements is to be obtained. So AC has been selected and this is the B. So B multiplying to K will get a 3 by 3 matrix. This is A and this is AC. So let us see. BK is this when we evaluate that product, and this is A minus AC. Now we have these 6 equations. One this, one this, one this, and these 3 here. So these 6 equations give the solution of K like this. And with this K, A minus BK equal to AC, we will obtain that AC which was shown just a while back here, and it will have the desired characteristic equation with this K. We can select a different AC which is done here. This is different AC, however its characteristic equation is also same as that, S cube plus 6s square plus 11s plus 6. Same characteristic equation this matrix also has. And when we set up the equation that B times K, this is B, this is K, this is A, this is AC, BK equal to A minus AC, we get a different set of course this left hand side is same but right hand side values are now different. So because of that we get a different K. This K is different than the K which we obtained a little while back. So we can get in this manner by different choices of the AC matrix, the closed loop system matrix, different values of K. One more thing, specifically for this example, I was telling that we have to pick up the consistent equations. Here if you see this BK, that product is coming in this form. The first row is coming 0. So we are constrained in this case to choose one AC matrix so that A minus AC will give first row 0. That must happen. This and this, they must be equal. Otherwise, there is no consistency. So in this case, consistent set will be obtained only by choice of one AC in which the first row will be identical to the first row of the A matrix. Otherwise, we will not get consistent set of equations. In this particular example, that holds, and this kind of situation may arise. We have to be careful while choosing the AC matrix. Now, we have a few remarks I have been telling, but we recall some of them. In case of multiple input systems, we have flexibility in design because we can select different AC for the same characteristic polynomials, and so we get different values of K. So we get design flexibility for the same characteristic polynomial. However, this poses a difficulty also because when we have enormity of solutions, then we have to obviously think which solution is better than the other solution, or which solution is the best among the different solutions. And for doing that, for arriving an answer to that, there is no direct path here. We have to probably do a transient response analysis for all those closed loop systems, and we have to select one of the better designs or the best design by looking at the transient response. Other way one can look is that probably one can look for fault tolerance. A design which is more fault tolerant, more robust will be preferred compared to the other design. So based on some additional criterion, one has to select a better design. Otherwise, in case of MI systems, there is enough flexibility. We move further and we try to address the question which must have, surely many of you would have thought, that how to choose the desired characteristic equation, or how to choose the desired location of closed loop system poles. And before we actually come to the guidelines which have been evolved, we see the governing points, the points which we should reckon. And the first point is that the control law, which is minus kx plus r, you see, if k is larger, then even for a small deviation, a large input may be obtained. Not very necessary, but generally. That this product k1x1 plus k1x2 and that summation, etc., which leads to u, will generally be large if k are large. So what it means, if the input is large, means that there will be a heavy actuator involved. In the system, the actuator will be heavier. So weight consideration, and of course it may be costly. A larger actuator will be costlier compared to a smaller actuator. So by this consideration, a small gain k would be preferred. The designs which yield a smaller gain, that will be preferred. Other consideration is, if the poles are to be moved further, then generally a larger k will be required. For example, we see, suppose we have a system x dot equal to 2x plus u. Now if we take that pole should go at minus 1, then u should be minus 3x, or the gain should be 3, minus 3. If the pole has to go at minus 2, the closed loop system pole, then u will be minus 4x, meaning that gain is 4. So in this manner we can see for higher order system also, generally what we find, that if the poles are to be moved more relative to their open loop locations, then the k values are large. Also, those who are familiar with root locus, they will recall that for k equal to 0, the poles are at the open loop locations, and as the k increases, the poles move away and away from the original locations. So if we choose a design in which the poles have to be moved much more away from their respective open loop locations, then larger and larger k will be required. And this translates to this, larger cost and weight of the actuator. And because many times we may not be able to change the actuator in the system may be unalterable, I mean the process system, the given physical system. So it will mean saturation of the actuator. The actuator will saturate at a smaller deviation of states from their equilibrium values or normal values. Other consideration is, again, those who have knowledge of root locus, they will easily comprehend this point, that the For k equal to 0, the poles are the same as the open loop poles. And as k increases, the poles move to the zeros of the system. And if there are fewer zeros than the poles, then some of the poles will move to infinity. So the poles which move to infinity, that is fine. They will move away and away as k increases. However, the poles which are going towards the zeros of the system, they will go only up to zeros even for infinite k. So what will happen, that if k is changed slightly, the pole will move further from its open loop location. Again, by changing k, it will move further. But as it has gone closer to the zero, further movement will entail larger and larger change in k. And to reach the zero, we have to literally have infinite k. What does it mean? That increasing k may not actually shift the poles, because poles will go only up to zeros. So we have to keep this point also into the mind by selecting the open loop, selecting the closed loop pole locations or coefficients of the characteristic equation. Then this comes from the transient response considerations, and also the next point, that the poles which are farther to the left in the S-plane, they govern the control amplitude. How much the control will achieve its maximum amplitude, that is governed by the poles which are much away onto the left. This is the left side. This is the S-plane. And the speed of response is governed by the poles which are closer to this imaginary axis, closer to the origin in this region. And the maximum control amplitude by the poles away. So we have to keep these 2 points also in the mind. And based on all these considerations, there are criteria. And these criteria, among these are these 4 I have picked up: dominant second order design, the ITAE design, the Bessel filter prototype design, and Butterworth polynomials based design. One by one we see what we do. In the dominant second order design, what we do is, as we know that the poles closer to the imaginary axis, this is the imaginary axis, this is the real axis. The poles closer to the imaginary axis will be dominant in deciding the system response. So many times we want that a higher order system, its closed loop, we want it to behave as a second order system. So what we do is, we choose the pole locations so as to give required bandwidth and the damping. So we choose the pole locations so as to give required damping, that omega n, and the required cos theta, or the damping. And the remaining poles we choose away relative to these locations, larger away in this side of the S-plane. So they will not be dominant. These 2 poles will decide the transient performance characteristics, and that means that we can achieve required overshoot, damping, settling time, etc. for this higher order system also, and it will behave like, essentially like a second order system having poles at these locations. This is the dominant second order design. In the ITEA design, the emphasis is to minimize a performance index of this kind, integral 0 to infinity t times absolute value of error into dt. And this gives polynomials of this kind. If we have to have a first order system, we have to select a bandwidth omega 0, from bandwidth omega 0 will come. If we have second order system, then this will be the pole locations, complex conjugate pair like this, one here, other here. If we have a third order system, a complex conjugate pair and a pole on the real axis. So this gives the ITAE design. When we take Bessel filter type design, then its pole locations are like this. Again, the omega 0 has to be selected. For n equal to 2, we have again a pair of complex conjugate poles, but different from what we have in the previous one. In the third order also, we have a slightly different one like this. So the Bessel filter prototype design, its main characteristic is it yields a transient response which will not have overshoot. So if the requirement is that there should not be any overshoot, we should go for Bessel filter type of design. The last one is the Butterworth type polynomials that can be selected, and in this it is like this. This is the sigma, this is j omega axis. If the system is of order 1, then the pole has to be selected at omega 0 like this. If the system is of order 2, then 2 poles are to be selected at 45 degree angle. This angle is 45 degrees. And they will fall on the semicircle with radius omega 0. So one will be here, other will be here. When we have to select 3 poles, then again they will be on the semicircle, but one will be here, one will be here, one will be here, making 60 degrees. When we have to select 4 poles, then they will be again on the semicircle of radius omega 0, but at 2 on this side, 2 on this side, making 45 degrees from each end. In this manner, the poles can be selected. However, we see for higher order systems, what will happen? Poles will come very close to the imaginary axis, and that is to be avoided. So additional constraint can be put that we don't want pole in some region very close to the j omega axis, the imaginary axis, so that the dominant pole will have a good damping. That is the consideration. Now with this, we summarize the chapter. We have seen that state feedback in classical perspective gives a feedback compensator like configuration. And the objective of pole placement methods is to achieve a desired characteristic polynomial. State feedback, if the system is controllable, it gives the closed loop pole locations and the desired characteristic polynomial. Any arbitrary choice is possible to achieve. We have seen that control gains for state feedback gain in case of companion form systems are easily determined through n equations, each one in separate variable. We have pole placement formulae for single input systems. So when we have to design control gains for single input systems, we can use Ackermann's and Bass and Gura formula. And we have guiding prototype design based on second order dominant, ITAE, Bessel, Butterworth prototype designs. So we can use that. Just another remark I want to make before we close this chapter is that the controllability is a must, we have seen, in order to design the control gains based on state feedback. Controllability is necessary requirement. And for higher order systems, because of ill conditioning may happen, the Ackermann's formula may not give good results. It may have numerical difficulties. So may happen when we transform the system to the companion form. So we will, in practical situations, we face difficulties in doing pole placement by either directly or through companion form or through formulae. We face the difficulties and we have to solve these challenges through some other means. Of course, in case of multiple input systems, we have a lot of flexibility in design, and some additional considerations must be brought in to converge to one choice of design. So thank you very much. We will meet again in another lecture.